All right. So this is our. We have one more topic in chapter 8 after this one, but what we're going to do today is we are going to talk about a method with the highfalutin name, the method of undetermined coefficients. Of course, what the method of undetermined coefficients really means is guess and check. This is a guess and check method. Now, I will say that the book has a very elegant development of how this actually works. It's called the method of annihilators. It views looking at differential equations as linear operators acting on functions. That will show up in later classes if you go on from this class and you start looking at the Laplace transform. So like in 344, I might teach annihilators. But yeah, it's just easier for the sorts of things we're doing for linear differential equations to do a sort of a cut down version of this with really predictable outcomes. So the observation that I want to make here is that if we start with a linear differential equation, so if I have a non-homogeneous linear differential equation, so of the form Ly is equal to f of x, I'm going to revisit this idea. These are normally called forcing functions, and I'll make that more clear at the end of the class today, and then we'll see it a lot more when we talk about chapter 8.5 next week. So if I have an equation that is non-homogeneous, so there's something that's not zero here, the general solution looks like y is equal to yp plus yh, where yh is called the homogeneous solution, and it solves the equation Ly is equal to 0. So part of it is the stuff that the differential equation turns into nothing, like the plus c when you're integrating. And yp is called the particular solution. And that gives this is a specific function with the property that L of yp is equal to f of x. This is always going to have arbitrary constants. And this will have no arbitrary constants. This is going to be a specific function. So you can think about this as being the bit that solves the exact differential equation, and then this is the part that is susceptible to initial conditions in a problem that looks like that. So we're going to start with a class of functions today where I can guess, based on the forcing function, based on the f of x, I can guess the form of the particular solution. And that's what we call the method of undetermined coefficients. So we're going to start with some examples here, and then I'll write down a table of all the guesses. And then at the end of the class, I'm going to get to talk about resonance, which is my favorite part of all of this. So I think resonance is a really cool idea. And also the sort of thing that as a working scientist or engineer, you should be aware of. Okay, so let's consider the differential equation y prime prime plus 16y is equal to 7e to the 3x. So if I was trying to solve this differential equation, the first thing that I would do, knowing that I have to form a homogeneous and particular solution, and because knowing the homogeneous solution is going to guide my guesses later for the particular solution, I'm first going to solve the equation y prime prime plus 16y is equal to 0. So I'm going to solve the homogeneous equation first. Of course, the auxiliary equation here, so what is the auxiliary polynomial?
R
squared
16.
plus 16 is equal to 0.
So plus or minus 4i.
R is plus or minus 4i. And so my homogeneous solution YH is going to be C1 times the cosine of 4x plus C2 times the sine of 4x. All right, so that's what we did last time. No more work than this is needed to justify this answer for you guys. Yep.
So if there was a number like a 1 plus that 1,
Then there would be an exponential in front here. So if there had been a 1 plus 4i, there would be an e to the x in front of both of them.
e to the x. Okay.
Yep. Okay. And we'll talk a lot more about that when we do the mass spring stuff in chapter 8.5, because that will correspond to the existence of a damping term in the equation. Okay, so now I have to guess where am I going to get a particular solution. So if you think about the left-hand side of a differential equation as a machine that eats a function, produces derivatives, and then adds them all back up together again, the only way that such a machine could spit out an e to the 3x by taking derivatives and adding the derivatives together is if I fed it an e to the 3x. Nothing else has e to the 3x as a derivative. So if I want e to the 3x to come out of this machine, I better stick in e to the 3x. Now I don't know what its coefficient should be, and that's why we call this the method of undetermined coefficients. So I'm just going to make a guess, or as the book likes to call it, a trial solution. It's a guess. So I'm going to guess, or rather form the trial solution y particular is equal to some undetermined coefficient times e to the 3x. So I'm guessing the answer has that form because that's the only way that any sort of e to the 3x is going to come out the other side. And this quantity, this a right here, this is what we mean by the undetermined coefficient. So the process that we're going to engage in now to find what that undetermined coefficient must be, at the end it should remind you a lot of when you did partial fractions and you got two polynomials to compare and you compared the coefficients of like terms. That's essentially what we're going to be doing here. Okay, so I want to take this and I want to be able to plug it into the left-hand side. So to get more specific data, I should probably take its derivative and its second derivative, since we have a second order equation. And now I'm going to take that unknown data and I'm going to stab it into the left side of the equation. So that gets me, let's see, y double prime was 9a e to the 3x plus 16 times y, which was a e to the 3x. And that's all supposed to be equal to 7 e to the 3x. Now I'm not going to mix the sides of the equation together. Ultimately what I'm going to be doing is comparing like terms. This gets me 25a e to the 3x is equal to 7 e to the 3x. And we don't need to think about dividing by e to the 3x or anything. When we're doing these solutions to these things, if there's multiple terms, I just need to compare coefficients of like terms. So 7 must be the same as 25a is a consequence here, because those are the coefficients of the e to the x's on both sides. So 25a is equal to 7, which means the original a that we guessed, if it had been 7 over 25, this equation would have been true. And so the conclusion is, now that we have determined the undetermined coefficient, the conclusion is, therefore, the particular solution must be 7/25 e to the 3x. We found it. If it's an exam scenario, you can always check your answer by plugging that back into the left-hand side and making sure that it produces the right output. What that tells us then is that the general solution to this differential equation, y is equal to the homogeneous solution, c1 cosine of 4x plus c2 sine of 4x plus the particular solution, which is 7/25 e to the 3x. And if you want to think about this in sort of an input situation, input-output scenario, this is all of the stuff that the differential equation turned into 0, because that's what it means to be part of the homogeneous solution. And this is the part that got turned into the 7e to the 3x. It's like a little howling at me out there. Must be really liking this particular solution. Okay, So basically, for the next couple of examples we're doing, I'm just going to give other things that could be here in the place of this function, and the guesses that you would make to discover them. All right. So I'm going to leave that for a second, people to finish up, and then I'm going to erase this board, I think. So we're going to start with the same function. I'm going to change the forcing function this time. This. Okay, so another possibility is that I could have a differential equation, y double prime plus 16y is equal to, and now I'm going to put, I don't know, how about x right here? Or hell, how about x plus 1? So now I have a situation where I have a polynomial over here. The homogeneous equation doesn't change. YH is equal to C1 cosine of 4x plus C2 sine of 4x. I think about this as being sort of, one way of thinking about this from a physical standpoint is that this is intrinsic. This is a solution that corresponds to the natural behavior of whatever it is that you're modeling. It's unacted on by an external force, what the system does. In this case, as we'll see, this is going to turn out to model a mass spring system. So what that's telling you is, if there was no force here at all acting on the system, and you took a mass spring system and you pulled the mass down and let it go, this is what its natural behavior would be. It would just do this forever. In the absence of external force, a mass spring system likes to oscillate. This guy, which I call the forcing function, you should think about this as extrinsic. The forcing function is imposing more structure or more behavior onto the system than was originally there. If a mass spring system is wobbling and you start just randomly shaking it up and down while it's wobbling, it's not going to do what it naturally wants to do. It's going to respond to the force that you act on it with. So the forcing function is extrinsic. And it results in an extrinsic solution, which is what the particular function represents. In this case, while eventually you will have a table, I mean, the book has a table, you have to memorize these because there's only 3 cases to memorize. What sort of object could possibly result in a polynomial if I fed it into a differential equation that takes derivatives and adds them together? Another polynomial. In fact, I can get away with, well, what polynomial should I guess here?
X plus 1?
You just want to guess x plus 1?
No.
Well, we could guess.
Third degree polynomial.
We could pick a third. You want to do a third degree? All right, let's do a third degree. A naught plus a1. I'll tell, and the logic makes sense here. A third degree polynomial, if you took its second derivative, would drop down to a first degree polynomial, right? So let's guess a naught plus a1x plus a2x squared plus a3x to the third. That's going to be our guess this time, because that's the sort of thing that if I stuck it into the differential equation and I took some derivatives, I could possibly get out a polynomial of the form x plus 1. Polynomial in, polynomial out. All right, so y particular prime is going to be a1 plus 2a2x plus 3a3x squared. It's a second order equation, so I better take another derivative. 2a2 plus 6a3x. I think I've done that correctly. Should make sure you verify my derivatives today, because what we're going to do is in the next step that's longer. All right. So if I take that information and I put it in the differential equation, I get, okay, so y double prime, that was 2a2 plus 6a3x. That was y double prime. Oh, no, 6a3x like this. Plus 16 times y, which, oh gosh, a naught plus a1x plus a2x squared plus a3x to the third. And that's all supposed to be equal to x plus 1. All right. So now I'm going to sort this out. This is supposed to remind you of when you did partial fractions and you've got to compare like terms. If you collect all the constants together, you get, what, 2a2 plus 16a naught, that's the constant. And then for the x term, we have a 6a3 and an a1. And for the squared term, we just have 16a2. And for the cube term, we have a 16a3. I think that's right. And now we just compare coefficients by setting up equations. So 2a2 plus 16a naught must be equal to the constant term 1. 2a2 plus 16a naught, the constant term on the left side, must be equal to the constant term on the right. The coefficient of the x must match the coefficient of the x. So 6a to the third plus a, did I miss a 16? I did. Sorry, there's a 16 here that I dropped. 16a1 is equal to 1. And then we got some really easy equations. 16a2 is equal to 0, and 16a3 is equal to 0. So what that tells me is I didn't even need the x squared or x cubed terms in my original guess. Right? I didn't need those. At least in this case. So this says, now we're going to determine the undetermined coefficients. A3 is 0, and A2 is 0. But if A3 is equal to 0, then that's 0, and that means A1 is 1 over 16. And if A2 is 0, then that means A naught is 1 over 16. So I've determined all the undetermined coefficients, and that means that my particular guess should have been at the beginning, or what the exact form of my particular solution is 1/16 plus 1/16 of an x. That particular solution gave me the right answer.
So did you only have to originally guess?
I could have just guessed. In fact, this is going to be the general rule. Is I only need to guess like.
As much as.
Yeah, the reason is because if there were higher order terms in here that were left over, if like the highest order term is going to get canceled, right? Because even if there was a y prime here, there's going to be one of them. So you can stop at whatever the order of whatever came out the other side was.
Okay.
All right. So again, your general solution is going to look like whatever.
C1 cosine 4x.
Yeah, y is c1 cosine of 4x plus c2 sine of 4x plus a 16th of x plus a 16th. All right. So before I go on to the next part, I'm going to write down the table. This is in my notes. It's in the book as well. Essentially what we're going to do is, based on the form of the forcing function, you always know what the guess should be. So here's like the table of guesses. The forcing function and the trial solution. And I'm going to leave another column for here for reasons that will become clear in a second. If I have a forcing function that looks like an exponential, then probably I should guess the particular solution an exponential with the same exponent. So if I see this on the right-hand side of the equation, this should be my guess for a particular solution. I want to re-emphasize the only reason this works is because we are assuming that our equations have constant coefficients. Okay, I'll give you an example of one that doesn't, and all hell breaks loose. If I see a trig function over here, so this is a frequent thing to come at physical systems, I might have something like c times the cosine of bx as my forcing function, or c times the sine of bx. Because sines and cosines have derivatives that flip back and forth, when I make my guess for the particular solution here, I need to include both a sine and a cosine term. And then finally, if I have a term of the form constant times x to the k, like the one we just had, where we put an x plus 1 here, then our guess for a particular solution is going to be a polynomial that stops when we get to the kth power. So y particular is a naught plus a1x plus ak x to the k. And that's pretty straightforward. Exponential out corresponds to exponential in. Trig function out should be trig functions in. Polynomial out means polynomial in. Where this is more interesting is when your guesses don't work. So let's look at the same problem again. Oh, actually, before I do that, let me talk about like a scenario where this absolutely just doesn't work at all. If instead I've given you the equation, so this is an example that doesn't work, that these methods don't work on. So one of the fundamental equations of optics looks like this. This is called Airy's equation. So notice, this does not have constant coefficients. There's an x here instead, right? As soon as I put that single x into this problem, I break every single thing we've learned about differential equations. All of it. Nothing works. In fact, the solutions to this, the two linearly independent solutions, are both power series that don't have closed forms. If you like to mess around with that, I'm really looking forward to doing 344 with you, where we'll actually derive how to solve these if you assume the solutions are power series instead. So this requires a whole other pile of methods like series. So tiny modifications to the differential equation blows up everything we know. So a good question to ask might be, well, if it's that easy to break these things, that's a pretty simple example. Why are we studying the easy ones that we're studying? Is it just because they have answers? And it's going to turn out to be the case that, in part, yes, this is why physicists and engineers study things, is because you can solve them. But a better answer is I'm going to show you, I'm going to start today and I will show you next week that the equations we're studying naturally arise by taking Hooke's law, which is about springs, force is equal to k times displacement, or Kirchhoff's law, which is about circuits, voltage is equal to current times resistance. Both of those equations, when you sort of derive the differential equations that they imply, they look exactly like the ones we've been studying. So those turn into equations that look like this. I'll put a B here. Right? Where those are constants. So the constant coefficient equations are sort of fundamental, and that's why we're spending so much time on them. Okay, so now we get to talk about one of my favorite topics inside here. So we're going to revisit the same exact equation again. Y double prime plus 16y. But this time, I'm going to ask this thing to produce 4 times the cosine of 4x. That's a totally reasonable equation. And before we go in, I want you to go into this with a physical intuition about what we're doing. This equation is going to describe a spring that oscillates naturally with frequency 4 over 2 pi. Right? The solutions to this look like y homogeneous is c1 cosine of 4x plus c2 times the sine of 4x. In the absence of external forces, what this spring wants to do is oscillate with this period. 2 pi over b, right? 2 pi over 4. Right, so pi over 2. But we're driving the system with a forcing function that has the same frequency. So we have a spring that wants to oscillate with this frequency, but we're applying an external force with the same frequency. Now, a scenario that you may have encountered recently or sometime in your past this is like pushing someone on a swing. Right? If you're always pushing, like you don't apply force until they're going away from you, and then that's when you apply the push, you're only ever contributing to the swing. If you're pushing them at the bottom and you're counteracting the swing, then you're not acting with them. But if I'm always pushing at the same frequency they're swinging at, the swings get bigger. So what you might anticipate is going to happen here is, if this wants to oscillate with this particular period, and I'm driving it with a force that oscillates at the same period, somehow that energy is going to be adding up. You might anticipate that that's going to be what happens in the answer to this. Okay, now we're going to consult our table over there, and we'll say, I know what my particular solution should be. I had a trig function come out. My guess, my sort of initial guess for the particular solution is going to be y particular is a times the cosine of 4x plus b times the sine of 4x, because after all, those are the sort of functions that would have cosines and sines as derivatives. Do you see an issue with that guess?
It's gonna end up being 0, is what I'm saying.
It's already like the y.
Yeah. This is already going to get sent to 0. These things are in the homogeneous solution. If you took this and you took its derivatives and you plugged it into the differential equation, you will have the bone-jarring disappointment of realizing you got 0 out. Because you've just fed the differential equation stuff that you already know it sends to 0. So it's a bad guess. Oops. Bad guess. It's part of the homogeneous solution. So what we do is we go over to our table and we add another column called modified trial solutions. If I have a guess that I'm trying to make that is part of the homogeneous solution, it won't work. So the modification we make is we just chuck in an x. So a sort of one way of viewing why this is justified is this guess for a particular solution will still have the right sort of derivatives, because the product rule will still give e to the ax's out. Right? There will still be things that have the right form when you do this. A higher level justification is due to something called variation of parameters, which is a technique for extracting solutions from other solutions to a differential equation, which is beyond the scope of what I can show you guys. So the whole theme of differential equations is the reason we do things is because they work. And 400 years of people chucking ideas at these problems have determined a set of methods that just do the job. So the job is, if that didn't work, toss in an x. How do I modify this? I chuck in an x. A x cosine of 4x plus b x sine of 4x. That didn't work? Chuck in an x. X times a naught plus ak x to the k.
Wait. Oh, I'm just the x on the outside.
Yeah, you can just take the x on the outside. What if that doesn't work either?
Chuck on another x.
Chuck on another x. You just keep chucking x's on until you get something that works. Okay, so if we go back over here and we're looking at this equation, I can't use this particular guess because it was part of the homogeneous solution. So I'm going to come up with a new guess, which is going to be the modification of this particular solution. So our modified guess is going to be y particular is equal to ax cosine of 4x plus bx sine of 4x. And those are not part of the homogeneous solution. So those won't get destroyed. And maybe, I have suggested this, and I'm going to do a bunch of math on the board now, and if this wasn't going to work, that wouldn't be justified. So by the logic of math professors, this must be the way to do it. All right. Make sure that you're following my derivatives here, because I want to screw this up. Okay, so the derivative of this thing is a times the cosine of 4x plus minus 4ax sine of 4x plus b times the sine of 4x plus 4bx times the cosine of 4x. I think that's right. And the second derivative, oh man, okay, there's gonna be a lot of terms on this one, so I gotta make some space here. All right. Second derivative. 4a, no, is it 4a minus 4a cosine of 4x? Sine of 4, thank you. Minus 4a sine of 4x. That's for taking the first product rule here. And then I'm going to have a minus 16ax cosine of 4x. I think.
Yes.
And then the derivative of that term is going to be 4b cosine of 4x. And then I'm going to get another 4b cosine of 4x from this guy taking the derivative of the x, but then it'll be a minus 16bx times the sine of 4x. Now, because we're ultimately lazy, the thing that we're going to try to plug this into is going to be y double prime plus 16y is equal to 4 times the cosine of 4x. I want to add this to 16 of those. And since I'm on the board and I have the chalk, I'm just going to put 16s on everything. Right? That's true. I mean, that's what I need. I need 16 y's, right? So I'm just going to, I can get 16 of them. Okay, now what happens if I add... What's that? Things do cancel out. This is so the whole point of this is when I start adding the second derivative to 16 times the first, lots of stuff here should cancel. If I add this line to this one, I will be adding y double prime to 16y, and what survives? Well, there's a 16ax cosine of 4x and a minus 16ax cosine of 4x. That term and this term are gone when you do that. There's a 16bx sine of 4x and a negative 16bx sine of 4x. That term is gone. So what you're left with when you add these things together is this whole left-hand side turns into minus 8a times the sine of 4x plus 8b times the cosine of 4x is equal to 4 times the cosine of 4x. So after I've simplified by pulling these terms together, I can determine the coefficients now. What's a?
0.
What's b?
Half.
So I know the answer. So I've started with a modified guess. I've extracted the coefficients. I've got a solvable equation. And the result is the following. So I started with y double prime plus 16y is equal to 4 times the cosine of 4x. I have now figured out that the particular solution is, okay, so if a was 0 and b is 1/2, then we're looking at the particular solution is 1/2 of x times the sine of 4x. That's our particular solution we extracted from our coefficients here. Right? Because our original assumption was ax cosine of 4x plus bx sine of 4x. A was 0, b was 1/2. And so our general solution is c1 cosine of 4x plus c2 sine of 4x plus 1/2 x times the sine of 4x. So this stuff, that just oscillates. C1 and C2 are constant. Whatever that does, it does forever. It has a fixed amplitude, a fixed period. This stuff is just kind of doing what it does. It's the natural oscillation of the system, right? Cosine and sine with a fixed amplitude and fixed phase shift doing its thing. This term has all kinds of bad things happening. So this is definitely bad. This is usually, not always, but this is usually bad news.
Can you graph that?
Yes.
Can you graph that?
What is the behavior of this as x goes to infinity? The sine of 4x part is easy. What does that do?
Keeps all steady.
But it's being multiplied by x.
So its amplitude is x.
So there's a envelope for this function. And y equals x, and then y equals minus x. And what the sine function is doing, what that term does, is it does this.
So how does that add on to the other stuff?
Well, this stuff has constant amplitude. And this stuff has ever increasing amplitude. This is an example of what's called harmonic resonance. So this is what happens when you have harmonic resonance. That is, we are driving the system with a force that has the same frequency that the system already wants to vibrate at. So, for example, if you set up a whole family of tuning forks in a room, and then you start playing like a note on a piano, the one that will vibrate the most is the one that they all have sort of natural frequencies they want to vibrate at, right? So if you start them not vibrating and you play a note on a piano, you're going to get a lot of response in the one that has the same frequency as the driving force, the note in the air that it's like vibrating in response to. Okay. Now this isn't always bad news. This is the way that, I don't know if you ever thought about this before, if you know, but essentially the way that a radio tuner works. A radio tuner basically says, I have a signal in the air that is being put out by a radio station. You can think of that as a wave, a forcing function. And what the dial on a radio does is it tunes the differential equation until the circuit oscillates at the same frequency. The circuit resonates, which amplifies the signal. So an amplifier is amplifying that resonance by tuning the circuit until it amplifies correctly, until it resonates correctly. Or in the story I told about the guys trying to shake down the dorm at MIT, instead of tuning the building, you just build a giant speaker and you sweep the frequency until everything starts to vibrate and fall apart.
How did they figure out that they built it?
Pretty much, you can hear this, if you've ever played the experiment of, in fact, I encourage you to do this. Go in a stairwell of one of the big buildings, like one of the closed-in stairwells, and just hum, sing a note, and sweep the note until you hear the stairwell vibrating, and you'll have found it's resonant frequency when you do that. There will be certain notes that make the whole thing like really loud when you do that, and you have found the sort of frequency of that room when you do that. Okay. All right. So a natural question to ask might be, how realistic is this? I mean, after all, this is not the way physical materials act, right? There's no free energy here. You can't just like tune your spring until it oscillates more and more wildly forever. And the answer is, normally what happens is the physical materials fall apart well before you've actually like had the, you can imagine in a spring system, at some point the spring fails, right? Or the building falls apart. Or in the case of, pretty much everybody knows this is not a real example, but there's that old video of the Tacoma Narrows Bridge, which is the deck bridge is oscillating like this. That is a standing wave in the bridge, which can result from things like harmonic resonance. A more fun example is there's a non-destructive interference that happened on the Golden Gate Bridge up in San Francisco. They put new deck plating on that has a bunch of little tiny holes in it. And when the wind blows across it, and I don't know if you've heard this or not, you can hear the bridge from across the bay. It hums. So when the wind blows across it, it sets up a harmonic standing wave on the bridge. There's this it's like they turned it into a giant whistle. So it hums. You can hear it from miles and miles and miles away. So generally harmonic resonance is not something you're shooting for in the system that you're studying. Yep.
Does the 1/2 mean anything at all, or no?
So you can think about what the 1/2 is doing. This doesn't contribute anything to the actual consequences of what's going on here. 1/2 modifies the slope of this function. So now instead of being x and x, it's 1/2 x and 1/2 x. But the problem is the amplitude is still ever increasing, right? So I'm going to give you a slightly different example that might be of interest for those of you that play a musical instrument, and this is another thing you need to be aware of when you're designing systems. You might try to dodge the issue by coming up with forcing functions that aren't quite the same frequency as what the system wants to vibrate at. So if I wrote down y double prime plus 16y is equal to 4 times the cosine of 4.1x, I don't want you to solve this by hand. Those 4.1s are going to be gnarly. Don't do that, right? But this actually, you can just guess the right. This works. You can guess the unmodified solution. Yp is equal to a times the cosine of 4.1x plus b times the sine of 4.1x. That works because that function is not part of the homogeneous solution. But when you go through the process of actually solving this thing and writing down the solution, it looks like this. So first, because the frequency of this forcing function is very close to the way this thing wants to vibrate anyway, what's a good way of describing this? If you ever sat in a car when it's raining and your windshield wipers are going and you can see the wipers in front of you and they're almost at the same frequency but not quite, like the wipers go together and then they separate slightly and all of a sudden they're doing this because they're exactly opposite, but then they'll slowly sort of line back up again where they're sort of constructively sort of, like they're out of phase and in phase, right? And the reason that happens is because they're almost the same frequency but not quite. So this sometimes acts in the same way that harmonic resonance does, and sometimes it acts opposite harmonic resonance. And so you get these things called these are beats. So every musician that's had a tuned instrument will be familiar with these. You get this sort of response where the system is bounded, but you get this envelope where the amplitude gets big and then small again. So in a sound, this would be like wah, 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 is what that would sound like. And if you've tuned a guitar or a stringed instrument before, where you've got two strings that are supposed to be the same note, but they're not, if they're exactly the same note, you don't hear these. If they're different just a little bit, you start hearing this beating because the signals are interfering with each other in this almost constructive way.
What do you mean, like two different strings on two different?
No. Imagine like on a guitar, like if
Yeah.
you see the way you tune a guitar is you play two notes on the same note on two different strings, and then turn the peg until they're the same.
Really?
Yeah. So you play A on one string, and the other string is an A string, and if the A's match, then you've tuned it.
Oh,
Okay. If they don't match, instead of getting like a clean sound, you hear this sort of wobbling kind of noise. So the way that you get rid of the wobble is you make them the same pitch, and then they interfere like this instead of like this. So also, by the way, I should point out, this is also considered a bad thing in most cases. I mean, yes, it oscillates for a while and then settles down, but the bridge that you built doesn't actually really like to oscillate wildly for a little bit and then calm back down again, right? This is not a typical sort of thing you want to have happen. I will also say all of the things that I'm talking about here, because the theory that we're going to be looking at applies to circuits, these are a pox when you're building circuits. Circuits are really easy to set up, like bizarre standing waves, like a disease, a plague,
Oh, okay.
right? So this plagues sort of amateur circuit building. You build a circuit and you accidentally set up resonance or near resonance in the circuit, and all kinds of like unexpected behavior can result from doing that, right? So I'm going to talk specifically about mass spring systems when we talk about 8.5 on Monday next week. Resonance is a really, really fundamental issue in all kinds of physical applications, so it's something to be aware of, and it arises naturally as a consequence of if every problem is a spring. I mean, the extent to which engineers and physicists and applied mathematicians think about this is literally everything is a spring. Like, oh, I got this long static material, how do I analyze it? Just think about it as a bunch of little springs all coupled together. I have chemicals interacting with each other in some sort of weird equilibrium. It's a spring oscillating back and forth. Like, it's all springs all the way down. That's basically the upshot. All right. Cool. So in 8.5 next week on Monday. On Thursday I'll do a fake test. Some of you are taking it early, and yeah, enjoy your math weekend.